Continue on the talk about these thermochemical materials degrading, and as Dr. Michael Adams has mentioned, for further studies and to be able to really survey different types of thermochemical materials, we'd like to apply this concept of rapid thermal cycling. So just to briefly review what we just learned, we would like to target this concept of long duration energy storage with these given storage and discharge durations, but we know that lithium-ion batteries at this discharge duration and storage duration is not really likely to happen. And at the magnitude we want it to happen, thermal energy storage is a much better option. And of those thermal energy storage candidates, thermochemical energy storage, we believe, is most suitable for our use case, essentially because of its higher volumetric energy density when compared to other modes of thermal energy storage in sensible and latent applications. Of those different thermochemical materials, we were looking at calcium carbonate, limestone, and the equation shown there demonstrates what happens in our reversible charge and discharge cycle, with the initial charging stage being the calcination, which always goes to completion, and the carbonation is where we discharge the heat that we stored in chemical potential. The degradation, or this the change in material from calcium oxide back up to calcium carbonate, we quantify using a dimensionless conversion ratio X denoted there. And most notably, for the focus of this presentation, we'll be looking at X subscript K, which is the kinetic conversion ratio that we have determined as the new standard that we should be looking at to compare different materials, other than the X subscript N, which is more a byproduct of longer reaction durations. And when we look at this conversion ratio, we note that it decreases with increasing cycle count, and thus we come to the conclusion that the cycling-induced degradation is the main mode of performance loss for thermochemical materials, because this conversion ratio ultimately is a direct representation of the decrease in storage capacity of these materials. However, literature has demonstrated that this rapidly decreasing conversion ratio from the first 10 cycles or up to 20 cycles is not really representative of what this material can actually do, because what's the point of a material of grid scale energy storage that only charges and discharges about 10 cycles, and it performs at 20% of its nominal capacity. And so we believe that the conversion ratio after this initial break-in period, so past that point up to where it becomes a steady state, is what we should actually be looking at to be able to compare different materials on a fair basis. Therefore, we'd like to be looking at 100 cycle plus, where the conversion ratio does not change anymore. And literature also has demonstrated that we can fit a somewhat accurate model to determine this residual conversion ratio at these points. However, this model is not entirely accurate, and we'd like to be able to experimentally demonstrate that this residual conversion at high cycle counts is actually real, depending on the model. And we would like to be able to reach that high cycle count so that we can do comparative analysis for practical use cases. Dr. Adams has mentioned also that we've been looking at a concept of thermal mitigation or thermal pretreatment, denoting that this permanent increase in conversion ratio increases with the number of short carbonation cycles followed by long carbonation cycles. However, we cannot really look into depth of like optimizing the number of short cycles or determining the frequency at which we should be applying this technology of thermal mitigation, essentially because we do not have the capacity to perform rapid and high throughput experimental methodologies to be able to determine at scale of gram scale pellets what happens at cycle counts past what is denoted in this figure here. Therefore, when we look at current thermal cycling methods that we could potentially use to work this out, notably we have TGA that Dr. Adams has mentioned before, where we note that it does have a relatively fast heating and cooling rate of around 20 degrees Celsius per minute. And at higher temperatures, when it cools, it can reach up to 50 degrees Celsius per minute. However, the sample scale that we're talking here is at the milligram scale, and for our case, we have been dealing with up to 20 and 30 milligrams per experiment, which is not at the point that we would like it to be. And also, looking at what we want to be looking at, benchmarking off of grid scale lithium-ion storage. We want to look at 3,000 cycles, but if we want to run that with a TGA, that would take about 8 months, and that's talking about one 18 milligram sample of one TCM, and so we cannot realistically perform a survey of different materials. Likewise for tube furnaces, although we have large samples that can go into a tube furnace, due to its high thermal mass, we cannot really reach a fast temperature ramp rate, and thus it also limits us by costing up to a year or more to perform a survey of one material of one sample. Therefore, we set out a target as a team to be able to combine the advantages and upgrade them such that we can perform gram scale high throughput experiments with fast thermal cycling rates, targeting about 100 cycles per day. Thus comes the concept of an accelerated reaction cycling. We have been calling it ARC. And this is inspired by these ultra-fast sintering and thermochemical synthesis techniques that use direct Joule heating with a porous carbon heating element, such that solid gas reactions are not hindered by the heating element. However, we introduced the capacity of adding individual gas ports so that we can control whatever fluid goes in and out of our reaction chamber. And as demonstrated here, we put it all inside a quartz tube with a Joule heater such that we can also monitor the process in case runaway happens and an immediate shutdown is necessary. We target a heating rate of around 23 degrees Celsius per second, comparing to 20 degrees Celsius per minute of conventional technologies. That's quite an improvement. That would allow us to reach about 13 minutes per cycle, and leading to about 3,080 cycles per month. And on top of that, because we are using a carbon heating element of around 50 millimeters in length and 17 millimeters in width, we can place these 300 milligram or 0.3 gram pellets, up to 4 of them at a time, and be able to run up to 1.2 grams of sample creation per experiment, which would then lead to about 60 samples within the TJ-DSC for further characterization. So what does this actually look like, right? So we take a carbon heating element, so just a piece of paper that conducts electricity, and it's quite stable. And we place a pellet on top of it, we adhere it with some high temperature adhesive. Then we put it on these bus bars that we designed out of stainless steel due to its high melting point, so it allows us flexibility in temperature points. We clamp it down, we place it into a quartz tube, and then we put it into the whole stainless steel chassis, which includes 3 gas ports, one for the reactive, one for the inert, and one supplementary in case you want to introduce a different gas for reaction kinetics control. And then an exhaust port. We charge the body with a DC power supply. We attach a thermocouple directly onto the sample itself, all being monitored by a DAC and a controller, such that the set point is controlled by the PI controller, and it outputs a PWM signal, which then monitors the DC power supply's output to what we want it to be relative to the set point and current temperature point. So this is what it looks like when it actually is running. So as you can see, there's the chassis on each sides. We have a radiation shield. The top part is taken off just so that we can see. And if you look closely, there's a heating element clamped down by the 2 buses and a pellet sticking right on top of it. For this experiment, we just have 1 pellet that is around 0.3 grams at the same 80% of the theoretical density we discussed earlier. And you can see at the top there's a little dollop of adhesive that holds our thermocouple directly on the pellet, such that we monitor the actual pellet temperature and have an accurate reading of what reaction temperatures our sample reached. And thus, we had a successful 15-cycle accelerated reaction cycling case, where we were able to reach the desired set points and flow the gas properly for 15 charge-discharge cycles, with cycling times determined using the time constant analysis framework Dr. Adams just talked about. Unfortunately, we did have to add a 35-second temperature settling time per cycle, because we did notice that with the extremely reduced thermal load and the very powerful DC power supply, there is a bit of overshoot whenever we ramp up the temperature, but this can be attributed to lack of optimization within our control scheme. And so with that, that will be, this overshoot of about 100 degrees Celsius will be monitored better, and the 850 will be reached a little bit more stable in further cases. However, that still meant a per cycle time of 13.5 minutes and a temperature ramp rate of 20 degrees Celsius per second. But this was not enough. We wanted to look at if these arc cycled pellets were actually representative of how thermal cycling happens in a TGA DSC, and so we compared a final 16th cycle after the 15th cycle of arc reacting, compared to a TGA aged sample, TGA cycled sample, sorry, and we determined that the conversion ratio is actually comparable within the error range between the samples cycled between the TGA and ARC. And most importantly, the total experiment time decreased from 12 hours to 4 hours, but do note that this 4-hour mark is because we had 3.5 hours of ARC cycling and followed by a 30-minute TGA post-processing. And so realistically, we're looking at a 1/3 or less cycling time compared to what would have happened in a TGA DSC. This also enables us to be able to cycle 100 cycles within 22.5 hours, with reaching the target of 3,000 cycles within 28 days. And thus, we have successfully enabled a realistic experimental duration for surveying TCMs and allowing comparative analysis at the residual conversion, such that we can actually monitor and determine what the steady state or long-term performance characteristics are of different thermal energy storage materials. So in summary, we wanted to look at the residual conversion ratio and investigate how the optimization of TCM cycling conditions occur, but then we did not have the rapid and high throughput thermal cycling experimental equipment we would need for this to happen. Because conventional thermal cycling experiments that provide high sample throughput require significantly long experimental durations of up to a year at the cycle counts we're interested. Therefore, we developed an accelerated reaction cycling technique that uses joule heating and decrease the thermal mass quite a bit, such that high temperature ramp rates can be achieved. And in conjunction with the time constant analysis framework developed, we have decreased the experimental duration quite a bit. And ultimately, moving forward, we'd like to be able to demonstrate full on the 100 cycle characterization within a day without any problems. So just to recap, we've decreased the temperature ramp rate from 20 degrees Celsius per minute to 20 degrees Celsius per second, leading to a decrease from 118 minutes per cycle to 13.5 minutes per cycle. And ultimately, most importantly, we can cycle, instead of a powder or crucible filled with 20 milligrams of a sample material, we can then move on to a pellet, which is at 0.3 grams per pellet, up to 4 pellets for us. I'd like to acknowledge all my lab members that have helped in this endeavor under the guidance of Dr. Michael Adams and Dr. Jordan Kocher. I'd like to thank the U.S. Department of Energy and the Degrees team for allowing me to have this opportunity. Thank you.
Question, please.
I have missed some part. How much was the energy consumption of the ARC mechanism compared to TGA?
We are not at the stage where we want to be looking at the power consumption for this. For reference, we were flowing, the power input that we were using for our current sample was about 15 volts at 10 amps, and that's sustained over about 3.5 hours about. If that gives you a sense in reference to TJ-DSC, I'm not familiar with exactly what the power requirement for TJ-DSC is.
You looked at for a control system using like PID instead of a PI?
PID becomes relevant as far as we understand when you want to sustain steady state at a very long time. That's not exactly the use case that we are interested in because we have to go back and forth between two different set points. And so we have experimented with adding a differential gain to our controller, which was deemed as unnecessary complexity in our control scheme. We've experimented with many different settings in our power settings and our controller gains. And we've determined that PI is enough, and sometimes even depending on the stability of the system, a P gain alone is enough. Although the integral gain also helps you reach set points much more stably. Does that answer your question? Yeah.
So you're heating the sample from the bottom,
Correct. Yeah.
And then you said that your thermocouple is
at the
attached to the top of
Yeah.
the sample. So I know that your samples are about like an order of magnitude bigger than what you'd see in TGA-DSC. Is that right?
Well, the TJ-DSC data that we've produced and shown earlier was with same geometry of the pellet, same thickness, same density. So yeah, if we just look at this one, it is of the same density. It's just that it's the whole pellet instead of a cut section of the pellet.
Right. So, but you're looking at a larger sized sample in your ARC rapid cycler. Have you done any calculations to see if there's a significant temperature gradient within your sample between where you're heating it at the bottom, you're measuring the temperature at the top, or are you not worried about that degree of accuracy in terms of your temperature?
That is a concern that we have been thinking about. Also, when we're looking at this deviation within one pellet, one sample, we've cut four samples, four TJ samples out of the same pellet, and we discovered this error. And we do think that this has to do, one, with the temperature overshoot that was discussed earlier, and so we had a greater degree of stacked up sintering that degraded the material more than it should have in 15 cycles, and thus we have lower conversion ratio here. But also, like you said, because our thermocouple currently is sitting on the top of the pellet and we're only heating it from the bottom, we do suspect that the bottom and the top have some sort of a temperature gradient. And although it might not be so significant to like hundreds of degrees, that increase in temperature at the bottom compared to the top temperature, we do suspect is causing a level of sintering that has to be addressed in one way or another. And so moving forward, we are coming up with a new design of the sample module where we have thermocouple attached directly to the heating element itself. So we modulate the heating temperature itself rather than the pellet top surface temperature. We have been using the top surface temperature as like a bit of a safety metric at this point, mainly because having gas flow and power transmission within a stainless steel chassis with the thermocouple sticking inside already is slightly dangerous in case the thermocouple shorts the power. But then if we have it connected straight to the heating element, we've discovered that in the case of the thermocouple insulation burning off completely, it comes into contact with the bus bar and the heating element, and because it provides less electrical resistance, all power flows through there and causes pretty detrimental damage, and so we are coming up with methods that we can manage that. It's just that for the scope of the work that has been completed within the last year, we weren't able to find a stable solution to that problem.
Have you looked at a heating element with a resistance that changes with temperature, so you could directly measure the temperature of your heating element just based on its electrical properties without having an external thermocouple in it?
We have considered those options. It's just that we haven't been able to find the right one of the form factor that fits right inside our system design. If we went ahead and changed the way our system assembles together, it is possible that we fit those types of heaters inside. It's just that one that we can measure directly from the power input while also being porous was a difficult combination to find. Yeah. Yeah,
I have a question. So, the dashed lines are your error band.
that is correct.
Is that standard deviation or?
That is one standard deviation. Yeah.
Standard deviation. How many repetitions per sample?
This is 4 samples stacked on top of each other. Yeah. 4 samples from the same age pellet. Yeah.
Okay, any questions?